We all know that the building blocks of a matter are electrons and quarks. I mean, a matter is the combination of electrons and quarks. But have you ever thought that how the electrons and quarks are made by and how the forces work? How is it that an electron coming from the far reaches of the cosmos has exactly the same mass or charge as an electron in an apple? There is a theory that can answer these questions. That is quantum field theory. Let me explain it. To understand what is quantum field theory, we first need to understand what is quantum mechanics and what is field theory. I think I don't need to explain what is quantum mechanics as most of you knew it. But still, I am going to explain it briefly. Suppose there is an object which has definite position, but at the microscopic scale, a particle doesn't really have a position. Its presence is distributed throughout space with more or less probability. This description of particles as wave of probability is called quantum mechanics. Quantum mechanics allows us to describe the evolution of a particle over time. Now, let me explain the field theory. As we all know that like magnetic poles repel each other and unlike magnetic poles attract each other. But why does it happen? What exactly there between the empty space of these two magnets? Actually, it is not truly empty. There is a field between them, which is magnetic field. According to field theory, the universe is a combination of different fields. Now, if we join these two theories, it will produce quantum field theory. Quantum field theory describes all elementary particles as vibrational modes in fundamental fields that exist at all points in space and time through the universe, such as magnetic field, electric field, gravitational field, etc. In fact, each elementary particles have own fields, such as electron field, Higgs field, quark field, gluon field, etc. Physicists represent these fields with numbers. There are one or more numbers in each point of the space. In fact, these fields are divided differently according to the numbers needed to represent these fields. For example, Higgs field is a scalar field because there is one number needed to describe Higgs field in each point of the space. Like this, electric and magnetic fields are known as vector fields because these fields need both numbers and directions to describe each point of space. According to the Newton, gravitational field is also a vector field, but according to the Einstein, it is a tensor field. Because when energy is given to this field, then it becomes higher energy state. That is why ripples are created in this field, like water, and we say these ripples as particles. For example, when ripples are created in electric field, we say these ripples as electrons. Like this, when ripples are created in quark field, we say these particles as quark. These particles disappear when these ripples become silent. The positions of these fields where we give energy appear as particles, and when this energy spreads through these fields, then these particles are supposed to be moving. And sometimes we need more energy to create particles in such fields and sometimes less for such fields. In fact, the amount of energy needed to generate particles depends on mass of the particle. For example, Higgs boson is much heavier than electron.